Today we will see some new topic. I'll come back to that spectral theorem in a few classes if we sort out that. Today we'll prove what is called Neumann double commutative theorem. Okay? And double commutative theorem, Neumann double commutative theorem. So the statement of the theorem is something, see, when you do mathematics, you see that this is algebraic, this is analysis or something, this is topological or something. So this theorem says that there is not much difference. I mean, this says that there is a purely algebraic statement will be equivalent to some purely topological statement. And that's not actually surprising because we generate this topology through some algebraic relation, of course. So it's not very surprising, but still it's a beautiful result because many times when we want to use the algebraic picture or something, I mean, it is like something commutant or commutes with some set of operators. That is one statement. The another statement is closed in some topology. So these two are equivalent statement. So when we want to take the closure, you can actually take the double commutant or something. We use the algebraic relation, or I mean, so we can use one of them, and it's very nice. That leads to many nice properties when you study this subject, because you will find somewhere else or some other places also where some purely algebraic statement will be equivalent to some topological statement. So that's if you go deeper. So this says that, I mean, there's nothing algebraic or analysis about some, I mean, these subjects. Okay. So the statement is for something like if you have a algebra A, and then you define something called commutant, and if you take something double commutant, that is same as the closure with respect to some strong topology, strong topology. That is a statement. This statement is actually very similar to what you have already seen, very analogous to this. I mean, the analogy I will not be able to explain now in this course. It is something like if you have a subspace, H naught contained in H, it need not be closed subspace. M is contained in some subspace. Okay, then M closure is actually equal to M double per, something very similar to that. And you can actually match this relation in some particular cases. I mean, the other statement is some sort of generalization of this. I mean, in some sense, I mean, which I will not be able to explain now, but this is very analogous to this, very similar to this statement. So to define this, so we will work with Hilbert space. I mean, we will work with concrete objects. Okay? There is a way of defining abstract phenomenon algebra and show that this is actually equivalent to this and all that, but we will not do that. So for us, if we have some subset, S is something contained in B of H, then H is a Hilbert space and B of H is all bounded linear operators. Then we define S prime, which is called as commutant. Huh? No, star algebra is there. Yeah. Yeah. It needs to be star algebra, otherwise it will not work. Okay. So if you have I mean, it's important that it's a star algebra because you will see, because that is what the commutation relation and star relation will be connected. Okay. So S prime is a commutant of S. What it means is all those X in B of H or T in B of H, whatever you want. Because it's like algebra, we will use small letters X. Okay, we usually use T operator for T, but we will use X because it actually elements of some algebra. Okay, so X in B of H says that XS equal to Sx for all S in S. So X is any subset of B of H. Then we define the commutant is all elements in B of H with commutes with S. Then S double commutant is to take the S commutant or commutant. Okay. So first notice that S commutant for any set S B of H, S commutant is Actually, I defined weak topology, if you remember. We can say it, I mean, we can make the statement with weak topology or strong topology, it doesn't matter. So we have the following topologies on B of H. In B of H, we have norm topology. We have the following topology. One is norm topology. Two, we have used the strong topology, which is Tn converges to T strongly, which is equivalent to saying that Tn xi converges to T xi. Norm means norm topology. That's well known. Okay, for all xi in H. This is the strong topology. There is something called weak topology. This is not actually weak topology, Banach space weak topology. This is what is called operator weak topology. This is a confusion of the terminology. We say that Tn converges to T weakly, operator weak topology, if Tn xi eta converges to T xi eta. It is the point-wise convergence happens in the weak topology of the Hilbert space. Okay? This is point-wise convergence. Strong topology is point-wise convergence. Here, the point-wise convergence happens in weak topology of the Hilbert space for all xi eta. These are all topology. You can actually, explicitly write the open sets. Explicitly write the neighborhoods, the base of the topology. Okay, I will come to that when we work with that. Okay? So this is the convergence. This is defined through convergence. If you want, you can use net. I have used sequence, but you have to use net because these are all not metrizable topology. Okay, for xi eta and h. Okay, this is the operator weak topology. Then S commutant is a weakly closed algebra. S commutant is weakly closed and it's a subalgebra. Yeah. It's clearly a algebra. It's clearly a subalgebra. If x commutes with s, x plus y will commute with s, and x times y will commute with s, x times y will go past that, lambda times will pass that. So clearly a subalgebra. Okay. Clearly a subalgebra. Okay. And all we have to see that it's weakly closed. That follows because multiplication is, multiplication is not jointly continuous in weak topology or strong topology, but it is closed in, it is continuous in, that is, if T lambda converges to T weakly, then T lambda S converges to Ts weakly for all S. In fact, if T lambda converges to T in strong topology, then both of them. And this thing I think we have seen already. If T lambda, first let us work with strong topology. T lambda converges to T. The strong topology means this goes to this. Okay. Then if you have then it is true for all xi. You can insert a S here, you can insert a S here. This is true for that also. On the other hand, if you insert here, this is continuous, so that will pass through. Because S is continuous, S of T lambda converges T lambda. This is a vector, T lambda xi converges to T xi. So S of T lambda xi will converge to S of T xi. Okay. So this will work for, because that's a vector. On the other hand, this works for all xi, so it should work for Si also. Okay. So multiplication is separately continuous in the strong topology. Multiplication is separately continuous in the weak topology also. That is, if T lambda S converges to Ts weakly, if T lambda converges to, this means T lambda xi eta converges to T lambda xi eta for all xi eta, right? You can insert Si. This implies T lambda S xi eta. This is another vector. So this will certainly converge to T lambda S xi eta. right? This is psi is just another vector. So for all psi and eta, so this implies T lambda S converges to Ts for all weakly. Okay. Similarly, if you have a S here, you can take that as S star here, right? And S here, S star here. So similarly, St lambda converges to S weakly. But then this is the Hausdorff topology. Okay. This is Hausdorff topology because the limit is, I mean, we can explicitly write the neighborhood. I will write the neighborhood here. For strong topology, the base is this. You fix a, I mean, these are like open balls. What I'm going to write is like open balls. I mean, not open balls. This is the, I mean, analogous objects of open ball. So you fix a x in, you fix a t in B of h, and xi1 up to xn in h, and be epsilon greater than 0. Usually for a open ball, we will fix one element and an epsilon. This is a topology on B of h. So if you have a metric space for an open ball, you will have fix an element in the metric space and an epsilon. Here you have a fixed element in T, and then these are all these are, I mean, instead of one open, I mean, we need these elements also. I mean, this is like open ball. See all those S in B of H. You take only one xi such that T minus S xi is less than epsilon. Okay. This is like this is open there. You take finite intersection of this, that will give a base for this topology. Then you take the arbitrary union. Okay, so that will be the base for arbitrary. Then you take the arbitrary, that will be the topology. Okay, so if you take finite, if you take finite intersection, you will have different xi is different epsilon, but you can replace the whole everything with the smallest epsilon. Okay, you can take the smallest epsilon. So this is the neighborhood. A neighborhood is something like this. N, you can, I mean, N is for a neighborhood, or you can use B or something. B of T with xi1 up to xn with epsilon. This is equal to all those S in B of H, such that T minus S xi is less than epsilon for all I greater than. This relation for one thing, I mean, if you have norm topology, it is just this. But strong topology, you need to choose xi1 up to xn and do it. This is the, I mean, so the strong topology is given by this neighborhood. So if you want to work with sequence or something converges to something in the sequence, then given epsilon, you will find a neighborhood in this. I mean, you need not take a open, I mean, in a metric space convergence, you need not take a neighborhood. You need not take an open set. You can take an open ball. In topological space, you have to define through open set. Okay, so this neighborhood you can work with. It's like open, it replaces the open ball of the metric space. Similarly, for weak topology, by weak topology, I mean operator weak topology, the neighborhood is again a T, and xi1 up to xn, and eta1 up to eta n, and an epsilon. That's what. This will have more elements. That's all. So that is, this is equal to all those S in B of H, such that mod of T minus S xi eta j is less than epsilon, something like this. Okay. And you can see that the limit will be unique if you take this. Okay. You can, it's an exercise. Limit is unique means it's a Hausdorff topology. Okay, so that's what we use. So because the limit is unique, as you can check in this here, I mean, this implies ST equal to 2S. That is, if you take a net in this, I want to prove that if you have a S in B of H, then S commutant is weakly closed. So if you have a net in S commutant, okay, T lambda, which converges to T, each T lambda commutes with S, then the limit will also commute with that. Because this will, I mean, the limit will be same. Anyway, this you can check easily. Okay, so if you have any S contained in B of H, then S commutant is a weakly closed subalgebra. Okay. Okay. And okay, I should have said something else there. Anyway, I'll come to that. Okay. So corollary or whatever next proposition is, if S contained in B of H and S is equal to S star, where S star is all those T star in B of H, where T is in S. Okay? You take the star of all elements. That is just S is closed under star. Okay. Then S prime is a star weakly closed star algebra. Star algebra. Okay. So S prime is a weakly closed star algebra means if some element is in S prime, then the star is also there. Some element is S prime means it commutes with all elements in S. Okay. If you take the star, I mean, but then it will commute with the star also. The star is also there. So it will commute to the star. By taking star, you will get the star will commute with that, right? So this is clear. Okay. So if S is in B of H, then S prime is a weakly closed subalgebra. The next thing you notice is you can define the nth commutant as I mean, you can go on like this, right? You have S from S you get S commutant. S commutant is S double prime. S double prime commutant is S triple prime. Okay? And you can go on. So S nth commutant is S n minus 1 commutant prime. Okay? It's a S n minus 1 commutant. But then this there is no need to do this because of the following. Yes, double commutant is X commutant is equal to S triple commutant. Okay? And from that, it's I mean all even commutants are. I mean S need not be equal to S double commutant, but S commutant is S triple commutant. The fourth commutant is same as double commutant, and then all even commutants are same except the zeroth one. All even commutants are same, and all S commutant S to N commutant is S to M to commutant. Okay? And similarly, odd commutants are same. Okay? So why this is clear? This should be clear. This is because so I should have added something wrong. Maybe I will add it here. If S, maybe A is contained in B, all are contained in B of H, then B commutant is contained in A commutant, right? Something A is contained in B, something commutes with B, then it will commute with A. So something is in B commutant, that will commute with A. So B commutant should be commuted. It will be reversed. Okay. So because of that, S is contained in, so now you have S. See, no. S commutes with S commutant, right? S commutant is all those elements commutes with S. So S should commute with S commutant. So S will commute with S commutant, right? So S is contained in S double commutant. Okay. Now this implies S triple commutant is contained in S commutant using that relation. S is contained in S double commutant. So S triple commutant is contained in S double commutant. On the other hand, this one, S is contained in S double commutant. That actually means that S commutant, I mean, applying instead of S, use S commutant. This is contained in S triple commutant, right? S is contained in S double commutant. Instead of S, use S prime. So that means this. So this thing implies that S commutant is S triple commutant. Now it follows, everything follows. Okay. So only S may not be equal to S double commutant. Otherwise, all even commutants are same, all odd commutants are same. Now we will come to the important relation. So that x is in B of h, some element, okay? And h naught is a subset of closed subspace. Okay? I use x because I'm going to use for s later, so that's why. Okay. Then x h naught is contained in h naught. That is, h naught is invariant under x. Okay. This is equivalent to saying, and P be the projection. P is a projection from h to h naught. Okay, the projection. Given a subspace, closed subspace, we associate a projection, and it is P be that projection. Then x leaves h naught invariant if this is equivalent to saying Pxp equal to, I think it is Px. Xp or Px. We will compute it and it will be clear. Okay. So we have h naught contained in h. That means h naught direct sum h naught per will look like h, right? So any operator T on h can be written as a matrix containing operators in T, h naught, operator in h naught per, and operator between h naught to h naught per, operator h naught to h naught per. So T in B of h, T will look like some T1, T2, T3, T4. It may be T11, T12, T21, T22. Okay. Where Tij is an operator from, so this will be H2. So Hj to Hi. Then I should have called it H1, H2. I mean, you call this H1, H2, okay? I mean, it's clear what it means, okay? This is H1, this is H2, then it will look like this, okay? So this just says that H21 is the operator from here to here. So T is invariant under that means what? So x h naught is contained in h naught is equivalent to saying, I mean, and x is equal to this x11, x12, x21, x22. Okay? This just means that x21 equal to 0, right? So x should, I mean, it should leave it invariant. It can take the perp inside that, but it should not take right now. This is the h22. So this will take this to here, right? So x is equal to yes, x11, x12, x21, x22. Okay? This is 0. Sorry. So now P is this projection, right? Okay. And if you take Pxp, that is just going to be x11, 0, 0. On the other hand, xp equal to xp or px? Px, I think. 1, 0, 0, 0, 1, 2, 0, x22. x11 you will get. And then here you get, but x12 you will get, right? So if you put xp here, I have written it correctly. 11, x12, x. Say it again. Pxp equal to xp. Yeah. So that's what I'm calculating. Yeah. So that's what I'm trying to see, and then I'm getting that. When I use that, I'm not getting it. So now if you compute xp, no, so 1, 0, 0, Now you get this is equal to x11 and x12, this is 0. And here the x21 is x21 is x21 is 0. Sorry, here it's 0. So it's 0, yeah, this one. On the other hand, if pxp equal to px, then that will imply that this has to be 0. Okay, xp, if you take it, I mean, this is the point. If you take any x11, x12, x21, x22, okay, then this is x. Then pxp equal to xp is equivalent to saying x21 is 0. Okay, which is same as that. Okay, so this is okay. That's all. So the corollary is S is contained in B of H, any subset, and H is equal to H star. Okay. And H naught contained in H closed subspace. Okay. Then X H naught is contained in H naught for all X in S implies, and P is a projection. P is from H to H naught projection. This implies P should be in S common. I mean, that will follow. I mean, proof. This is equivalent to this. Okay. This is for all X in H. That is for one single operator. This is for all X in S. Okay. So X H naught is contained in H naught. This implies X H naught perp is also contained in H naught perp. Since this is for all X in S. Since S equal to S star. Okay. X H naught contained in X H naught implies X star H naught contained in H naught, X star H naught perp contained in H naught perp. This is a basic relation. This is linear algebra. But since it is star closed, you can use just X itself. Okay. So now from these two equations, we get that X coming, I mean, XP equal to PX for all. This will imply that XP equal to PX for all X in S. X leaves invariant means, I mean, one way, if X leaves H naught and both of them invariant means, it has to look like this, some element here, some element, both of them will be 0. Okay. On the hand, if both of them are 0, then it will come out with that. Okay. Okay. So now let us state the theorem. So it is just this statement. If some set, star closed set, okay, leaves a subspace invariant, okay, then the projection, that is equivalent to saying the projection is in the commutant of that set. It is just this property we'll use. Say it again. X H naught is contained in H naught. X H naught perp is contained in H naught perp. X has to look like this. Okay. This has to be 0, this has to be 0, because it cannot take something from that, something. On the other hand, if this holds, then that holds. Right? So it's because of star closed. Okay. So this is the theorem. This theorem is called Neumann density theorem. Density theorem. Okay. Which says the following. A contained in V of H is a star algebra, need not be closed. Okay? Then A closure with respect to strong topology, strong closure. Incidentally, I forgot to say, I proved that S commutant is weakly closed. That implies it is strongly closed. Because strong topology is stronger than weak topology. Norm topology is stronger than strong topology. See, if you have a convergence in the stronger topology, not this strong, forget about that. If you have a stronger topology, which contains all the open sets of the weaker topology, if something converges in the strong topology, then it will converge in the weak topology, right? Right. So if something is weakly closed, that means what? Something converges in that topology, the limit will be there. Suppose something in the strong topology, that will converge in the weak topology, so the element will be there already. So any weakly closed subset will be the strongly closed. So if something is weakly closed, it will be strongly closed, it will be norm closed also. Okay. So if we have a star algebra, if it is strongly closed, it's a sister algebra also. Sister algebra is just a norm closed star algebra. So it will be automatically a sister algebra also. Okay. So you take the A strong closure topology, which is just I'm taking the topological closure with respect to strong topology. That is nothing but A double commutator. So this is the density there. I mean, this is actually this is in a sense double commutator theorem. This says that as a corollary, you will get something is strongly closed if and only if A equal to A double commutator. Okay. Strongly closed means this closure is A. Okay. So A equal to A double commutator. But this is a statement you will prove. So this is a topological statement. You take the closure of a star algebra, okay, and then that is equal to A double commutator, commutator of the commutator. Okay. We already know that this is strongly closed. We already know any commutator is strongly closed. Okay, that we have already proved. So A is contained in A double commutator, which we know. Okay, so this is the left-hand side. LHS is contained in A double commutator. So, this is a strongly closed algebra. This is just a closure, smallest strongly closed subset containing this. So, this should be contained in that. Okay. So, the strong closure of this is contained there. We only have to prove that this is contained here, or we have to prove that A is, we only need to prove A is strongly dense. Dense in A double commutator. Okay. That's what we have to prove. So we have to prove that the strong closure of this is equal to A double commutator, since A is certainly contained in that. So we only have to prove if you take this is strongly dense here. That is, you take any element here and take any strong neighborhood that has to contain an element from that. That's what this says, right? So any neighborhood, we can work with the base element. You need not take any open set. The actual statement is you take any element and an open set around it, that should be there. But any open set will contain the so-called neighborhood. So only we need to prove, enough to prove for any, so maybe I call it X tilde X tilde I don't want to use. So maybe Z in A double commutator. I take an element in double commutator. Okay. So enough to prove for any Z in double commutator and vectors Xi1 up to Xin in H and epsilon greater than 0. Okay. There exists a X in A such that we need to show that it is in the neighborhood. That is, Z is in this neighborhood. Z is in the neighborhood. So it has to satisfy this condition. That is such that norm of Z, X minus Z, Z minus X, doesn't matter. Xi is less than X for all. Okay. This is what we need to prove. So here comes a trick. Actually, this trick is much easier when you know something called tensor product. Since we haven't done, we will use a matrix trick. Okay. I will say it also, since even though we haven't done, I will tell you that also. Okay. So we want to proof of the claim. Okay, this is enough to prove this. You call it claim or something. Claim. This is the claim which we need to prove. I call it a claim. Okay. So proof of the claim. Proof for n equal to 1. I mean, you have xi1 up to n elements, and an epsilon greater than 0. You are given a z, you have to find. You are given an arbitrary z, you have to find a x in A. Okay. I assume that n equal to 1. I assume I want to prove for n equal to 1. I'm not going to use induction. I'm going to do some amplification. Prove the statement for n equal to 1. Then use that for a different, some amplification of this. Okay. So for n equal to 1, so we need to prove, so if we have z in A, double comitant, we want x in A such that for n equal to 1, that is, you have a xi in H and epsilon greater than 0, and z is in epsilon, we want a x in A such that x in A such that z minus x xi is less than epsilon. That's what we want to do. Okay. It is in that ball. It's in the epsilon ball of xi. So how do we get that? So for that, I define this h naught is equal to all those. I have fixed a xi here. I have an epsilon. Okay. So fixed a xi here. I take x xi, x in E. Okay. And you take the closure, of course, with respect to the inner product. Okay. I mean, not equal to this is topology in the Hilbert space. Okay. This is in H. So now we will use that statement we have already. That will follow immediately. This is something like, this is what is called A xi closure. I apply, not A. That's it. A xi. You fix a xi, act the whole algebra on this, and then take the closure. Okay. Now P be the projection H naught. Okay. Now you notice that x H naught is equal to x y xi. Okay. Where y is A. Right? You take, you take an element in that. Notice if you have some, I want to take a, see, if you have a yz in H naught. Yz is, not all elements in H naught is going to look like that, but it's a closure of that. So dense set is there. Okay. Then xyz is also in H naught, right? Because that is ASI, right? So it takes a dense element inside that, so it has to leave that invariant, right? Because it is continuous, of course. So this implies x H naught is contained in H naught. By the previous, this is for all x in A. Okay. By what we have already proved, this implies that P is in A comitant. Right? P is in A comitant. Now Z is in A double comitant. Z is in A double comitant means it commutes with the elements in the comitant. So in particular, it has to commute with P. Okay. This implies Z of H naught is also contained in H naught. Okay. That is a statement. Okay. If some operator here leaves, something leaves the subspace invariant, This is true for all x in A. Okay. So because of that, we get this. P is in the commutant. Now Z is an element in the double commutant, so it is in the it commutes with P. Okay. This implies Z of H naught is also contained in H naught by whatever the lemma we have. Okay. I mean, Z P equal to P Z means P Z P is also P Z. Okay. That's, I mean, you don't confuse with that. Okay. So this in particular, is that Xi is in H naught. But H naught is the closure of all such elements. So there exists X in A such that Z Xi minus X Xi is less than epsilon. That's what it means. Okay. Z Xi is in H naught. Means that H naught is the closure of all such elements. So there is a X in A such that this happens. So the claim is proved for n equal to 1. Okay, now case 2, n is arbitrary. N is arbitrary. Now what we do is the following. Let Hn, you amplify the Hilbert space. Hn equal to H direction, H direction. You take the n times. Okay, H direction, H direction, H direction. Okay, like Hn. This is just take n times. This is actually equal to what is called H tensor Cn. If you use tensor product and if you know the theory, but then we have to prove all that. That will be, this is actually equivalent to that. Okay? Then it will all be simple, but then we have to prove many things, how the cometant looks and all that. Okay? So we directly write like this. So Hn looks like this. Okay, and given an element T in V of H, define, you write the amplification of the Tn. Any element, any operator in this Hn is a n cross n matrix with operators in B of H, right? Okay, I mean, this is going to take its operator, either H will be taken inside or H can be taken to one of these spaces, but that's also H. Okay, that's not different spaces. I mean, otherwise we have to use the Tij from Hi to Hi. I mean, if it is H1 direction up to Hn, then it will be Tij, where Tij is an operator from Hj to Hi. Okay, so here everything is H. We don't have to worry. So any operator on this space is an n cross n matrix with entries coming from B of H. Okay, in particular Tn, you write it as, for any T, you write it like this. Everywhere it's just a diagonal T. Okay, just diagonal. Diagonal entries with T. It's like a scalar matrix, and except that it's all one single operator. Okay. And you write An equal to all those Xn. I mean, you write An, Tn is T. An is A, if X is an element of A, then XXX. You just amplify it. Okay? You just write it as a matrix in the n cross. Then these are the two claims. Then claims. We have, this is just, I mean, A amplified A. Okay, you take A and write it as a diagonal element. An commutant is equal to, by writing this, I mean all matrix with entries coming from A commutant. This is all those Tij. Okay, the Tij is in A commutant. Okay, this is one first line. AN commutant will look like this. And AN double commutant is A double commutant N. Okay, this is the second statement. First statement, second statement. So we have A, the algebra, star algebra. We have amplified it to AN using but just the diagonal, just writing every element as the diagonal elements. Its commutant in the big Hilbert space, P of Hn, is just all matrix entry coming from A commutant. This is in B of H. This is in B of H. Any operator under B of Hn is a matrix with entries coming from B of H. This is M1, but the entries come from A commutant. Okay, that is what the commutant of this. On the other hand, AN double commutant. This is A double commutant N means you take an element in A double commutant and put it in the diagonal. Okay, this is A double commutant N, which is same as AN double commutant. This is A with, diagonal elements with coming from A. This is diagonal element coming from A double commutant. So this is the statement. So proof of 1. Actually, I should leave it as an exercise. First statement is if T is in AN commutant, okay, this commutes with this, means, what does it mean? T looks like Tij. Okay, that T equal to Tij. It will be a matrix like this. T looks like where Tij coming from B of H. Okay, the Tij is in B of H. See, we are doing mostly algebra. There is no analysis in this. They're just doing algebraic computation. Right? So Tij, so T is Tij, the Tij coming from B of H. And suppose T is in AN commutant. That just means you have the matrix Tij, which commutes with this elements. Which one? Why? T is an arbitrary element in AN commutant. Why you should like Ti? It is just an R. I'm just saying, I'm just going to compute it. Okay? T is just something in B of H with commutes with AN. I'm just computing it. Okay? It's just some element in AN. So Tij with some x like this. Okay? 0 everywhere is equal to again this x 0, then Tij. Okay. This, if you just multiply it, you will just Tij x you will get. Okay. Is equal to x Tij. That's what you get. So this implies Tij has to be in M1 A commutant, M1 of A commutant. On the other hand, this is equal to this will be equal to this. You can see. Okay. This is a matrix multiplication, nothing else. Okay. From that it will follow. So 1 is proved. Now we want to prove 2. Okay. So now suppose something in the double commutant of AN, that means it has to commute with this AN commutant. So AN commutant looks like this. So it commutes with that. Okay. So A is, forgot to say, A should be a unital algebra. I'm sorry. It's a star, not just star algebra, it's a unital algebra. When you write A double commutant, identity will be there, right? So the statement doesn't make sense. So identity has to be there. So this is what is called a Neumann algebra. Neumann algebra will always contain identity by definition. Okay? So the identity 1 is there in A. Okay. So in particular, this commutant, we want to compute this AN double commutant, but AN commutant looks like this. AN commutant looks like this. Okay. In particular, you can take A commutaton contains one anyway. I mean, here we are only using one actually. A commutaton only that contains one. So that one, you can take this element, no, one in the ijth entry, everywhere else zero. That element is here. I mean, this Mn of A commutaton, one is there. So ijth entry, one. Everywhere else zero. That is an element here. Okay. So let Eij equal to I mean Eij KL. Okay. I mean, this is Eij is fixed here. Okay. Ij is fixed here. Then KLth element is equal to delta Ij KL. Okay. This makes sense. Okay. These are what are called partial isometries. We haven't discussed it. Okay. This is, I mean, if it I equal to J, this is just the projection onto the nth subspace. Nth ith subspace. I equal to J. So I is, I mean, there's only I. Then there's a projection onto the ith subspace. Okay. Otherwise, it is just the, it takes from here to here. Any takes, it's permutes. Okay. If it is in the jth Hilbert space, that element will go to the ith Hilbert space. Okay. That's what Eij is. So, okay. Now let's some Z, I mean, let's say some Z tilde is in AN double commutaton, which is equal to Mn of A commutaton, okay, by definition. In particular, Z tilde of Eij equal to Eij Z tilde. If you multiply with Eij, you take a matrix 1 and the ijth element, everywhere else 0, it will pick up the ijth element of this and jth element of this. Okay. So, I mean, everywhere else it will be 0. We just multiply like this. Okay. So, it will imply that Z tilde ij equals 0 if I not equal to j. Okay, just matrix multiplication. You just check. Okay, this is just matrix multiplication. You just take a matrix with ijth element 1, everywhere else 0, multiply with any matrix. It will, if you take this way or that way, it will, in one side you will get the ijth element, other side you will get the jth element. Okay, whatever. So these two matrix should be 0. So I am in the, when I not equal to j, it should be 0. Okay. So only when, so this implies that Z tilde is equal to some, I mean, it will look like that. Okay. If you run up to Z, 0, 0. It will look like this. Okay. But then now it has to commute with all of that element, right? Why all of them should be same? No, it will take, no, it has to be, sorry, it has to be one single element. If you take this, yeah, if you take Z1 up to something, okay, if you multiply with ijth element, it will permute, no? Right? Ith element will come to jth element, right? Something like this, I think so. Like this. No, won't it come? Yeah, everything else will be 0. So it has to be the case that all of them should be same. We just write it, it will be clear, okay? It's just matrix multiplication, okay? Is that Ji delta? Correct. right? No, no, I didn't say that. That is not the case. You get a matrix where only element is here and the other element is here. This has to be here, you get 0. So this should be equal to this. This should be equal to this 0 here. If you multiply this, you just do the multiplication, okay? You just an exercise. When you multiply this, you will get only the entry will be in the ijth entry. Here it will be the jth entry. These two matrix has to be 0. Here you have 0. So it will be, this will be equal to 0. This should be equal to 0. Okay. And this is true for the diagonal elements also, right? Okay. So it has to be one single element. It will be given by one single element, z, z, z. Okay. So z delta will look like this. Now, because it commutes with M and A commutant, okay, now use that. Okay. But since now Z delta is in M and A commutant implies Z should be A double commutant. I should have given it as an assignment, but it's okay, I've done it. So this implies Z delta, this implies AN double commutant is A double commutant N. Okay. This is just a remark. In case you have seen tensor product in some other subjects or somewhere, what we have done is this AN, you have to take a x in B of H. I take H tensor Cn. Okay. On this, I take X tensor 1. I mean, no, this is not in H tensor 1. This is an operator. You can tensor the operators also. It will look like X tensor 1. Then the commutant of this will be 1 tensor something algebra here. Here you will get the whole of Mn. Here you will get the 1. I mean, here you will get the commutant of this element. Sorry. If you take A tensor 1, its commutants will be A prime tensor Mn. Anyway, let's not do all that. And just say it will be, the picture will be more clear when you use tensor product, okay, which we haven't done. So now it's clear, okay? Now by this matrix calculation, it's clear. Okay, so what we have is, if we have A, then AN delta. Now let us go back to our what we want actually. What we want, we have written it somewhere. We want the following. Okay? Originally, what we want? We have a Z in A double commutant and Xi1 up to Xin in H and epsilon greater than 0. We want, okay, there exists a X in A such that X minus Z Xi is less than epsilon for all I. Okay, this is what we want. Okay, we want to show that A is strongly dense in A double commutant. So we took an element here and we took a neighborhood and we want a X in that A, which is in that. Okay. We have proved for I equal to 1, we have proved this. Okay. I mean, for any algebra, for any vector, for anything, we have proved. Okay. So we have proved, so now applying case 1, case n equal to 1 to this vector. Which vector? An. Now An is an algebra in B of H. Okay. And we know that An double commutant is A double commutant N. Okay. So now I'm just going to, this statement is true for n equal to 1, right? For any algebra. So I apply that statement, replacing A by An and replacing the vector, we're replacing the operator Z by Zn and a vector, let Xin equal to Xi1 up to Xin. This is a direction in H direction H. Okay. You can take an element like this. And Zn is in an double comitant, and epsilon greater than 0. There exists a x n in an, right? Such that norm of this is the norm in the nth Hilbert space, I mean the direct sum Hilbert space. Zn minus xn minus this n, I mean the vector n. This norm is less than epsilon. I am applying the statement for this algebra, an algebra, instead of A, and this vector, one single vector in the amplified Hilbert space for the single vector, okay, and this epsilon. I have an x here. This just means, but then Zn is just Z, x is just x. This just implies that Z minus x, xi is less than epsilon for all I. Okay. This is just the norm square is equal to norm square of this, and that's why it's true. So we approve. Okay. Corollary. A contained in B of H, star algebra, unital star algebra, a star algebra is enough. Then 1, A equal to A double comitant. 2, A is strongly closed. A is weakly closed. A is strongly closed. A equal to A double comitant. We have already seen that any comitant is weakly closed. So this implies this. And weakly closed, of course, implies strongly closed. And strongly closed implies this. Okay. So this is true. So this is what is called a von Neumann algebra. Yes. Maybe I should write once full name. Okay. So a von Neumann algebra is characterized by these two properties. A equal to A double comitant, which is purely algebraic property, or it is strongly closed or weakly closed. There are some other topology called sigma weak topology, which I haven't defined, which is actually the weak topology of BFH. That is the actual weak topology. This is weak topology, but this is not weak topology. This is what is called operator weak topology. There is a Banach space weak topology. B of H is a dual space. Okay? There is a Banach space weak topology. Sorry, weak star topology. I'm sorry, not weak topology, weak star topology. Okay, B of H is a dual space. It's a dual of some space. It's actually dual of what are called trace class operators. I mean, I don't know whether you have to see in graduate analysis 1. There's 2 in BV's class. Okay, if you I hope you are attending that. Okay, so you will see that. So if you take the collection of trace class operators, dual is B of H. So it's a dual space. Okay, so every dual space has something called weak star topology. That weak star topology is what is called, I mean, that weak star topology convergence is what is called sigma weak convergence and sigma weak topology. It's just called sigma weak topology. So if this is also equivalent to that, closed in that topology also. Okay. So and you should know the topologies are different. For a subalgebra, they are all same, except norm topology. All these topologies are same. There is something called sigma strong topology and all that, but it's all equivalent for a star subalgebra. So this is the statement. So shall I go for some more time? Actually, I will not be able to take class on Friday, as I said, because the Ruptak, he is not here. He has some problem on Thursday. Okay, so I will not take on Thursday. Friday, I'm going somewhere, which I forgot completely. And I will not be here on Monday, Tuesday also. We will take the next class on Wednesday, 6:30. I think it's okay with him. This Wednesday, there is some, I want to take on this Wednesday, but some function is going on, no? I mean, something is going on. So maybe you want to attend, I also want to attend. So we will, this month, tomorrow we will have a class. Extra class instead of Friday. I thought we will not have extra class. Next week we will meet on Wednesday and Friday. We'll see an extra class later. I mean, we just wasted last week. I mean, we didn't take a class. So I will take some more time. Tomorrow also I will take more time. Okay, we want to see an example. What is an example of von Neumann algebra. In fact, we haven't seen examples of C-star algebras also. Okay, but you can take you took the representation of C of X, and you can take any subset. I mean, close it with a star. When you take the algebra generated by that, star algebra generated by any set, close it in the norm, you get C-star algebra. Similarly, you take any set S contained in P of H, okay, such that S equal to S star. Otherwise, you add it. Okay? S union S star, you can take it. Okay. Then you just take S double commutator. That will be the phenomenal algebra. But how do you know it's not equal to B of H? B of H is a phenomenal algebra. Everything is inside that. So, I mean, that's a universal. So, everything is there. So, but you need to know that S double, I mean, it's not equal to that. Okay. So, to construct those phenomenal algebra, we need to work. I mean, we need to do some work. Okay. But commutative phenomenal algebra is easy to construct. We have already seen. Okay. So, that's what I will prove, that it's a phenomenal algebra. Okay. So, that's what I want to prove. I want to prove the following. This is a more general statement. I will prove for a measure pi mu. I mean, I want to prove for L infinity and C of X, whatever. I will prove for C. I mean, we have this representation pi mu of C of X into B of L2 X mu, right? If you have a measure mu, then you have a L2 X mu, and if X is compact, I mean, all that we are, I'm assuming all that. It's compact metric space, something, okay? So then we have a pi mu like this, which is just the multiplication representation, okay? So I will prove for this representation, okay? For a general, every representation will be a direct sum of this representation repeated some finite number of times, and that we have proved already. You can go through that proof, and you write it for that assignment. But I will tell you the proof orally, okay? Write as assignment the following statement I'm going to make, okay? So this is the theorem or proposition. Okay. Pi is a representation of C of X into B of H. Okay, some pi. X is compact and all that. Okay. Then we know that pi tilde, there exists a measure mu on X. We know that, I mean, if this is the representation, then we will have a measure on the finite measure on X, such that pi tilde is a representation from Lx to mu to B of X. Okay. Such that pi tilde, I mean, I don't want to repeat the statement, I made it several times. Pi tilde is an extension of this pi, okay, and some strong, this will, which is unique extension in the sense that if you have a sequence in this, which is uniformly bounded, if it converges strongly, sorry, if it converges in measure, then it will converge in strongly in the image. Okay, so blah blah blah. The well-known, I mean, our earlier extension. Okay. Earlier extension. Okay. Then pi tilde of L infinity X mu, just the image, is a phenomenal algebra. Why? Because that is same as pi of C of X double commutator. You have a representation. I mean, you don't even need this statement. Okay? I'm just saying that you take, I mean, anyway, it's clear that you are taking a commutative set, subset. Okay. Now I'm just taking the double commutator. This is also commutative. That's really important. So it's not B of H. This is a pi tilde is, I mean, this image is abelian, right? So it's not everything. It's not B of H. So it's a proper subalgebra. It's a phenomenal algebra. Okay, this is the first example of a phenomenal algebra, proper phenomenal algebra. B of H is one example. C is one example. I mean, constant times identity is one example. Okay, the trivial examples. This is a non-trivial example. Okay, so what we do is you take any representation, then you have an extension pi tilde. Pi tilde, the L infinity is represented in B of H. That image is it's not, I'm not taking any closure or anything. Just take that image. That is exactly equal to pi of Cx double commutator. Okay. In fact, the earlier pi of Cx also is a sister algebra. It is just the image. How do you know it's closed? Because it's an isometry. It will be closed. Okay? Because the pi is an isometry, so the image will be closed. I mean, okay, if we need to know whether, I mean, in our earlier example, it's isometry. When it is isometry, it will be closed. Otherwise, it will anyway a contraction. So otherwise, if something converges, is it closed? Is clear? I think it's clear. Something converges in the image. That doesn't mean it converges here. So it's not clear anyway. When it is isometry, it's closed. Okay. It's still. Given the. Say it again. Given the abelian. That's true. Yeah. But what property you are using? I'm just wondering. So you look at the kernel. A by I. That's a closed ideal. Yeah. A by I. Yeah. We haven't used all that. So anyway, it will be the case. But here, at least for what we have done, when it's isometry, it's a sister algebra. Okay. So we want to prove this statement. Okay. So we know the following proof. See, we have used something called unitary equivalence of representation. That is, if you have two representation, pi 1, pi 2, they are unitarily equivalent if pi 1 of x is equal to some u of pi 2 x. I mean, pi 1 is on h1, okay? Pi 2 is on h2, okay? Then you have a unitary from h1 to h2 such that pi of x equal to u pi 1 pi 2x of, I mean, x is coming from some Caesar algebra, okay? U star. You have pi 1 a representation of Caesar algebra, pi 2 is another representation of Caesar algebra. They are said to be unitarily equivalent if it looks like this. I just want to, I have already remarked, I'm just saying it again that this is such a nice, the unitary equivalence is something like, it's like same representation. Because if you take, see, if you have some commutant, if you have some u, a commutant, okay, and if you take u star, that is same as u commutant. You can see that u star commutant. You can convince with that. I mean, this, see, you have one Hilbert space H1, okay, another Hilbert space H2. You have a unitary between them. This is not part of the proposition. I'm just telling you. Right? And if you then T going to UT U star, this is an isomorphism between B of H1 to B of H2. Okay? This will take an algebra to some other algebra here. And if we take the commutant here, it will be precisely the commutant here. Just write the relation, you will get it. And if something converges in norm, then u of that, I mean, this is what is called add u. Okay? This is T going to this is what is called add u of T. Okay? Add u of T equal to ut u star. This add u, if Tn converges to T, then add u of Tn will converge to add u of T in norm, in strong topology, in weak topology, anything. Okay? You can check it. Okay? I mean, you just write the definition, it will follow. Okay? So because of that, up to unitary equivalence, up to unitary equivalence, or pi is unitarily equivalent to unitary equivalence, pi will look like, any representation will look like direct sum of n equal to 1 to infinity pi n, where pi mu power n. You know what is pi mu power n? I mean, pi mu n power pi mu k power kn. We have proved this. We have proved Zahn's lemma, and we have used and we proved that, right? If you have any representation of C of x, if it is cyclic, it will be like pi mu. Okay? And if it is any representation, It is direct sum of cyclic representation. And maybe there may be some representation may repeat. So all repeating representation, we are just taking it here. Okay. And then all the others are different representation. Okay. Everything will look like this. Okay. Here pi mu kn means pi mu k is on right L2 of x mu k, right? Okay. Mu k n means you take it n direct sum and it's like a diagonal. Right? It's like a diagonal. I mean, whatever we use there, that a n or amplification. It is just the amplification. Okay. So I will prove this proposition for mu. Okay. Then for amplification, if you use the earlier idea, it will follow immediately. Whatever this statement. For a direct sum, you need to work a little bit. If you can't do it, we will do it in the class. What you have to do is, we proved a proposition where you use some set En and all. I will come to that. I will say talk about it in the end. I will come to that in the end. Okay. So up to this, it will look like this. So assume for the time being, case 1. Assume pi is equal to pi mu for some mu on Borel sigma algebra of x. Okay. I will prove this for this mu, and the assignment is for the general pi, where it looks like this. Okay, and I will give you the idea. I'll tell you the idea. Assignment is proving it for general pi. I will prove for pi mu. Using? Yeah, using this and then using this statement. Pi will direct sum like this. Yeah, yes, sir. Okay. So I am assuming pi equal to pi mu. So what is the representation? Pi mu is the representation of C of x to B of L2 of x mu, right? Where pi mu of any f acting on any g is in L2 and f is in C of x, is this fg. Okay. And we know this representation is a nice representation. So now what do I want to prove? I want to prove that C of x commutant, C of x double commutant is pi mu tilde of L infinity. Pi mu tilde is also multiplication representation, right? Okay, that's what we have seen. It is a multiplication representation which extends in that condition. Okay. So let A equal to pi mu of C of x. Okay. We want to prove A double commutant. Want to prove A double commutant. Want to prove. Okay. For the time being, A double commutant is A double commutant. We want to prove A double commutant equal to pi mu tilde of L infinity x mu. Where pi mu tilde is also multiplication representation. Okay. And we claim the following. And okay, so for the time being, we want to prove this. So let m equal to pi mu L infinity x mu. I mean, I want to prove m is equal to A double commutant. Okay. Here I have done A double commutant equal to this. That doesn't, this is what we want to prove. Okay, so I call this as, this is equal to this. I call this as m. Okay. Then I want to prove, all I want to prove is m is equal to A double commutant, where A is pi mu of C of x. Okay, A is pi mu of C of x. Then I take the A double commutant. I want to prove that A double commutant equal to this, which I call as m. Okay. So we claim the following. We claim something more. We actually prove that this m is an abelian. M is abelian. Okay. So m is contained in m commutant. M is abelian, right? M commutes with everything in M, so it's in the M commutant. Okay. We prove that M is equal to M commutant. It is maximal abelian. There is nothing more. If some other element, something which is not in M commutes with everything, then you can add it and that will also be abelian, right? You can take an element which commutes with this, one single element, and you can add it and take the phenomenon algebra generated by that will be abelian. Okay. So this says that M is maximal abelian. This is maximal abelian. Okay. So A double commutant, A, what we have, A is contained in M. Okay. So A double commutant, if M is equal to M double commutant, okay, M, see, one by one let us come. Suppose if I for M is equal to M double commutant, then, I mean, if this is true, if this claim is true, if the claim is true, if the claim is true, okay, then M is equal to M double commutant. M is contained in M double commutant. Okay. But this is the smallest phenomenon algebra contained in this, right? M double commutant, this is just a strong closure of this. So this is the smallest phenomenon algebra containing M. Now this is a phenomenon algebra containing equal to this M. Okay. Now this is equal to, so this is contained in M commutant. So this will imply that M equal to M double commutant equal to M commutant. Okay. These are all same. If we prove this, okay. In particular, this will imply that A double commutant is also this, because A is contained in M. Okay, so yeah, M commutant will contain, A is contained in M. M commutant will contained in A commutant. A double commutant will be contained in this, right? No, what I'm saying? No. A is contained in M. Sorry, wait. A is contained in M. Now A double commutant is a phenomenon algebra generated by A. But you can approximate anything in M strongly by elements in A, right? A double commutant contained M. Is it okay? Is clear? If you have anything in M, M is just this image. We have shown that if some continuous function, we know that some continuous function converges to that. I mean, what is the name of the theorem? I forgot. What is the name of the theorem? I used the theorem, no? If you have any L infinity, then you have continuous function converging to that, uniformly bounded, it converges in measure, something. We proved it. What is it? I forgot the name of the theorem. The theorem says that if you have L infinity function, then there exists sequence of continuous function, uniformly bounded, which converges to that in measure. It's just Lucy's theorem, no? Okay. It follows from Lucy's theorem, or is Lucy's theorem? Follows from Lucy's, yeah, Lucy's theorem. Okay. So because of that, anything in AM can be approximated strongly by elements in A. So M should be in A double commutant. Okay. So M is contained in A double commutant. Okay. And M double commutant will contain A commutant, and all those things are equal. So this implies that this is also equal to A double commutant. Okay. Because of that, because M can be approximated, strong closure of A will contain this. Okay. So the phenomenon algebra generated by A will contain M. Okay. So M is contained in A double commutant. Because of this, this is true. Okay. So we have proved the statement. Okay. So if we prove this, this is enough. M equal to M double commutant, all these things will follow. I mean, M equal to M commutant. That's what we have to prove. So for L infinity, you take, I mean, this is the only statement I'm going to prove. From that, all these things follow. Okay. So this statement is actually M is the maximal abelian subalgebra. This is abelian subalgebra, and it is equal to the commutant. So it is a maximal abelian subalgebra. Okay. Okay. So proof of claim. What is a claim? So something commutes with M. So T is in M commuton. Okay. Okay. T is in M commuton. So I want to get an element in M such that, I want to get a function here such that T is equal to pi mu of F, pi mu tilde. Okay. This is a tilde here. Okay. Want a phi in L infinity x mu such that T is equal to pi tilde of phi. Okay. This is what we want. Any guess? Can you guess the phi? We have this partial function 1. T is in M commuton. I want to prove that M equal to M prime. Okay. So, okay, let's go through one by one. Sorry. M is contained in M prime, right? All you have to prove is M equal to M prime. So, I have a T in M prime. I want to get a phi in L infinity such that T equal to phi of phi delta of phi. So, how to get that phi? That's all we want. So, you have 1 in L2 because it's a finite measure. Okay. Okay. Now, T of 1 is an L2 element, right? Sorry, it's mu. Okay. Equal to phi. This is, we have to show it's in L infinity. A priori, it is in L2. Okay. T of 1 is phi. It's a function, right? Our Hilbert space is a function space. Okay. So, T of 1 is phi. Okay. So, first we want to prove that this is in L infinity. And then we want to prove that pi mu of phi. It is just the T of any element is just multiplication with respect to this phi. That's what you have to do. Okay. So, first, suppose, now notice that L infinity of x mu is contained in L2 of x mu. It is dense, right? It is in fact dense. Simple functions are dense here, so L infinity is also dense here. You should remember C of x is dense here. Simple functions are dense here, L infinity is dense here, but C of x is not dense in L infinity. It's a statement about topology. L infinity is dense in L2 topology. Okay, this is the L2 topology. L infinity of the topology is L infinity topology. It is with respect to L2 topology, these functions are dense here. Okay, okay. If you take any function, L infinity function, that is in L2, and that set is dense here. Okay. If you want L infinity acting on 1, you can, then it makes sense, right? L infinity acting on 1 and okay. This is just not the right statement. It is something like pi mu of L infinity acting on 1. That is what I'm saying. That is dense here as subspace. Okay. That's the right statement. So let F is in L2 x mu intersection. I write it. I don't. If you want, you use it. You understand what I mean. Okay. This is a dense subspace. Okay. It is. This is actually contained in this, but okay, I take a F here. Then, what is T acting on F? T acting on F equal to T acting on. If you want, you write it as pi mu tilde. Okay. That's acting on 1. 1 is a constant function. Okay. 1 is constant function in this. Okay. Then T, this is the problem. Okay. Yeah. This is okay. F is a function. Okay. Now, T acting on F. F is a L2 function also. So I'm just applying T on acting on this. This is equal to T of pi mu tilde F acting on constant function 1, right? Pi mu tilde is just multiplication 1. Now, T commutes with M. So you can take it there. Okay, which is equal to pi mu tilde F T of 1. But T of 1 is phi. So this is just pi mu tilde of f acting on phi, which is equal to f. Okay, this is just the multiplication. Sorry, this is the f phi. Okay, no? F phi, phi f, both are same. Okay, phi f. This is just multiplication by phi. T is nothing but multiplication by phi on L infinity. We want to prove that phi is in L infinity, and it is actually multiplication on the whole of L2 also. See, now what we have proved is on a dense subspace, T is multiplication by phi. We have to prove that on whole of L2, this has to be but that will be the case because it is dense there. But all we have to prove is phi is in L infinity now. Okay, so we have to prove that phi is in L infinity. So for that, we have already seen this trick. Let ER is the set ER equal to all those S in X such that mod phi of S is greater than R. Okay, we want to show that this has measured 0 when R is greater than the norm of T. Okay, so mu of ER square equal to integral over ER. Okay, just this one function d mu. Okay, I mean this is a constant function 1 on this d mu. Notice that on ER1 ER, okay, maybe I just use it. On ER, okay, on ER 1 ER times R. I mean ER is something phi is greater than this, no? Phi of S, R is constant, phi of S. That's all, no? Phi of S is greater than this on 1 ER. Okay. So this is less than or equal to 1 ER phi, right? Let me write it in the terms of norm. This is equal to, I'm sorry, one second. I will put a half here, which is equal to norm of 1 ER. Okay, which is less than or equal to, if I use this, you get that phi of 1 ER norm. Okay, I'm just writing it in a different way. I just put a half here. Okay, so this is equal to T of, no, but we know that this is equal to T of ER. T of 1 ER, sorry, 1 ER. Okay, and because 1 ER is in L infinity, for the L infinity, it is just multiplication. We have proved, which is equal to T of 1 ER. This is less than or equal to norm T times norm of 1 ER. Again, I mean, this is the L2 norm. Okay, this is L2 norm. This is also L2 norm. This is norm of T times norm of 1 ER L2 norm. So this is norm of, which is actually equal to mu if you want, which is equal to again mu ER power half. So this implies when R is, I mean, when R is greater than norm T. Oh, sorry, there is a 1 by R somewhere. I forgot. Sorry. I'm sorry. This is R times this, no? So there has to be 1 by R here. Sorry. So this implies mu of ER equals 0 if R is greater than norm T. Okay. Fine. This is the same thing which we used earlier. It's a, I mean, if you want to calculate the norm, you can take approximate by a sequence, and it's a similar idea only. Okay. So mu of ER equal to 0, R is greater than this. So this implies mu of ER greater than 0 means phi is bounded, no? I mean, norm phi is, in fact, norm phi will be equal to norm T if you do the calculation again. This implies phi is in L infinity, right? This just means mu of ER equal to 0 after some time. When R is greater than this means, that's what the definition of L infinity. Phi is in L infinity, right? Phi is in L infinity means what? It is bounded. I mean, it's the measure. I mean, measure of set something greater than that should be bounded, right? There exists a R such that mu of that set is 0. Okay? So this implies that phi is in L infinity. So now we have proved that phi is L infinity, and it is a multiplication representation on a dense subspace. So there has to be a multiplication representation. This implies that T is equal to pi mu of phi. Since T coincides with the, so all our calculation implies that T is equal to pi tilde mu of phi on dense subspace, on L infinity, on we want pi mu tilde of L infinity acting on one, acting on one. Okay. So on a dense subspace, so this implies T tilde equal to pi mu of phi, pi mu tilde of phi. So what we have proved is M is equal to M comma. Now we have proved the proposition when pi equal to pi mu. If it is, forget about this, if it is same representation written n times, we use in the fundamental density theorem, we use a trick, no? You amplify it, then you compute the double comitant. That is just the double comitant element. This is just the diagonal elements. This pi mu k power n is pi mu k written n times, and the k n times or whatever, the diagonal elements. See? Its double comitant will be the double comitant of each one of them written in the diagonal elements, right? Double comitant of the whatever, the representation. So that proves the theorem, immediately proves the theorem. For the direct sum, you need to work. For the direct sum, what you will get is, this pi is on some direct sum of Hn. Okay? You take the projection onto Pn, Hn, Pn. That Pn will commute with that. That will be in the comitant. Okay? You can see that that's clear, no? If it is direct sum, it will commute with that. So double comitant means it has to commute with that Pn. If it has to commute with the Pn, it has to be again direct sum, something like that. So each direct sum you will get a phi, but you have to get a single phi. So that is the assignment. You will get a phi, you will have to get a single phi. How do you get a single phi? If you have a phi, direct sum of phi, how do you get a single phi? You go through the earlier proposition I have proved, where I will get a En, where it defines through Radon-Nikodym derivative and other things. If you remember that. You take that En, each phi will have a support in that En. Okay. So if you write that phi is equal to summation 1 En pn, you will get a phi. That phi will satisfy the required thing. So that is the assignment. Everything else I have said. Okay. We'll stop here.